All right, so the assignment is due on Tuesday, and today we're going to be talking about Bernoulli's equation. So the purpose of Euler's equation was to predict a change in pressure when we have an acceleration that is a local acceleration. Does anybody remember what kind of flow is associated with local acceleration? Unsteady flow. Now, Bernoulli's equation is going to be used to describe when we have non-uniform flow. So that's what we're headed in today, is in the direction of Bernoulli's equation. So what we've done so far is we're saying when there's local acceleration, meaning that the velocity is changing over time, then Euler's equation was allowing us to predict some change in piezometric pressure. So it's the change in pressure plus gamma z. Now, in contrast to that, Bernoulli's equation is concerned with how the changes in velocity with respect to position affect the pressure and elevation. So Bernoulli's equation is that some pressure at location 1 divided by the gamma plus z1, it's the elevation at a certain location, plus a velocity head term, v1 squared divided by 2g, relates to a situation at a second location. So each of these three terms at location 2. So what it says is that when you have a change in velocity with respect to position, then the sum of these three things have to remain constant. We'll talk about what each of those three terms means, and so this is going to be applied to position, changes in velocity with respect to position. In other words, when we have convective acceleration. Now there are a couple of assumptions and limitations that apply to Bernoulli's equation. And those are that, number one, this is applied when we have steady flow. So in other words, Bernoulli's equation is for non-uniform conditions, but we're assuming that there isn't also simultaneously unsteady conditions, meaning that the velocity is changing with respect to time. So for us to get accurate results in using Bernoulli's equation, we have to have steady flow. We're trying to isolate what the changes in pressure are due to, and in this case, we're saying that it's due to a convective acceleration, not also simultaneously a local acceleration. So limitation one is we have to have steady flow. The other is that we apply it along a streamline. Apply along a streamline. Now consider the types of cases that we're actually going to apply Bernoulli's equation to. Remember that when we worked with convective acceleration before, we had some sort of a nozzle where the velocity was increasing because flow was going through a converging section. So if we have a pipe where the diameter is decreasing, then what that means is the flow that enters at one velocity is going to exit at a much higher velocity because it's being forced through a smaller cross-sectional area. And if we put 1 liter of water into the inlet of this nozzle, 1 liter of water has to come out. There's no way that we can compress water inside of this control volume. Water is relatively incompressible, so what goes in has to come out. Now, it doesn't have to come out at the same velocity, though, and that's how we make it work. If the flow area is decreasing, then the velocity goes up. So here we have convective acceleration. And what we're saying is along a streamline means that the water that comes in, this arrow, is going to flow through here, and then it's going to exit around the top if we had laminar conditions. The flow in the center, the streamline here, is staying in the center as it goes through the nozzle. At the bottom, the streamline deflects a little bit, and then it comes out. So when we apply location 1 and location 2, this formula is saying we want to look at how conditions are changing at two different locations. They have to both be on the same streamline for us to accurately apply this equation. We couldn't say that we want location 1 to be on one streamline and location 2 to be on another. We have to apply it along the same streamline. The next limitation is that we're assuming it's an incompressible fluid. Now, water is relatively incompressible. It's a little bit compressible. Remember when we talked about bulk modulus for water? I mean, if we apply many gigapascals, we can get it to change a few percent in volume. But for the most part, water is a pretty ideal fluid to apply Bernoulli's equation to because it is incompressible. Gases, on the other hand, like air, are highly compressible. So what that means is that sometimes we'll have errors in applying Bernoulli's equation if, in reality, the fluid is compressing a little bit. Then there may be some changes in pressure that Bernoulli's equation isn't accounting for, because built into Bernoulli's equation is the assumption that this fluid we're applying the equation to is incompressible. The fourth limitation or assumption is we're assuming that the fluid is inviscid. An inviscid fluid. Anybody want to take a guess at what you think inviscid means? That's right. It's a fluid with no viscosity. So there's no such thing as a fluid with no viscosity. So I guess one way of looking at it is Bernoulli's equation is never right? Because your assumptions can never be satisfied. There's no fluid that's inviscid. Now, some fluids have a low viscosity, like gases, for instance, have a relatively low viscosity. Liquids, their viscosity is higher. So it's kind of interesting that actually when we've got a fluid that satisfies the incompressible, like a liquid, water is relatively incompressible, but it's bad at being inviscid. But then gases are good at being inviscid since they have a relatively low viscosity, but they sort of fail the incompressible test. So, I mean, you can never satisfy Bernoulli's equation, right? But the thing is that it's good enough in a lot of cases. We have a lot of situations where if we apply it over a relatively short distance, then the issues of inviscid fluid become less of an issue. Because the reason why in the fourth assumption we're saying we want this to be an inviscid fluid is that fluids that have viscosity are those that experience energy loss due to pipe friction. So the way that we get away with applying this for fluids that do have viscosity, like water, is if location 1 and location 2, if their distance apart is relatively short, then the effects of energy loss are minor. And then it doesn't matter so much that the fluid had viscosity. So that's kind of why it's okay to apply Bernoulli's equation to fluids like water, is that when we do apply it, we're not going to apply it over the course of miles. We're going to apply it over the course of maybe a few centimeters. And in the lab, we'll apply Bernoulli's equation, and we'll have fairly good luck with it. We'll send water through a contracting section. We're going to measure the pressure change. And what we actually observe in the lab pretty accurately conforms to what Bernoulli's equation will predict. So these are 4 limitations that you should commit to memory. It may be the sort of thing that I would ask about in an exam. We don't have quizzes in this class, but I used to ask about it in quizzes. Any questions about the nature of those 4 limitations? All right. Just to set the stage for how we apply Bernoulli's equation, let's discuss engineering models. A model is a representation of reality. So everybody here has seen the pipe rack in the lab. It's that piece of equipment that I said is kind of top heavy, and I said, don't push on it too hard, it may tip over. We don't study that pipe rack because there are lots of pipe racks out in the world that you need to know about. But rather, we study that because each one of those individual pipes represents an entire system out in reality. So if you study how a small segment of pipe behaves, then you can apply the behavior you learn about that one small thing and generalize it to much larger systems. And so that's an example of a model. The the prototype that we have in the lab is a model of a full-scale system. And the same thing is true about the types of models that go into wind tunnels. You can study the behavior of winglets at the end of an airplane wing by putting it into a wind tunnel and just using a small-scale clay model and making small changes to that relatively small model, and then see what the full-size prototype scaled behavior would look like. And so it's not just actual physical models that are important, but equations themselves can be models as well. So Bernoulli's equation is a model of what happens in reality. It's a way of predicting what the behavior is going to be based on some sort of a conceptual representation. Now Bernoulli's equation is a fundamental model. It's based on the first principles of physics. There are also empirical models, things that are just based on observations of data. Like if I gave you a model that said the range of an aircraft is equal to the fuel that you have on board divided by 4.37 minus 0.43 times the weight. That would just be kind of a coincidental relationship that was based on the fact that over time we had lots of little data points and we drew a line through those data points, and then there was some best fit equation that fit the data points to the line. So that's an empirical model, but fundamental models are usually more powerful because they have a more direct relationship to the laws of physics, and the way that you can often distinguish between the two is that in the case of this Bernoulli's equation, the units are consistent on the left-hand side of the equation and the right-hand side of the equation. The units here are all going to be meters. Z, or elevation, is measured in meters. Pressure is measured in newtons per meter squared. And then the unit weight is newtons per meter cubed. And so then that expression together, the newtons are going to cancel out, and then we have meters to the third divided by meter squared, so it's just meters. So we're adding meters to meters. The same thing is true of this velocity head term. If you look at velocity squared, then that's meters squared per second squared, and divide it by g, which is meters per second squared, then what's left is meters. So my point is that a fundamental equation is going to have consistent units, whereas an empirical equation, this 4.37 may just be like a unitless conversion factor or some sort of a slope coefficient that we have to just multiply it by the data in order to get things to fit, but it's not necessarily based on some observed law of physics. In order for us to apply models, we have to identify what is the boundary of the system, and the boundary of Bernoulli's equation is going to be not only just the location that we apply it, but also these limitations and assumptions we know that apply to it. So the boundary of this model includes the assumption of steady flow along a streamline for incompressible fluid that has no viscosity. The variables are the things that can change in the system, and then we also have parameters that are physical constants that don't change. And so the parameter of G, for example, is going to be a constant. For a fluid that if we're sticking in our system is always water, then gamma would also be a parameter that doesn't change. But then the variables that would be changing in Bernoulli's equation will be pressure, velocity, and elevation. So there are two main terms of Bernoulli's equation, and I've written it here on the right whiteboard in terms of, this is called in terms of head, which has units of meters. We can also write Bernoulli's equation in terms of pressure. And so there's the piezometric pressure and the kinetic pressure. So you remember that piezometric pressure, P sub z, is pressure plus gamma z. And then the kinetic pressure term is going to be the density times the velocity squared, kinetic pressure density times velocity squared divided by 2. What we're saying is that along a streamline, the sum of those two terms is constant. So here at location 1, if you know the elevation above some datum, if we say here is our elevation datum, our z datum, doesn't necessarily matter where, as long as both location 1 and location 2 were measuring the z above that point, what we're saying is that the sum of the piezometric pressure and the sum of the kinetic pressure between two locations will be equal. It's just that the energy is changing forms. Okay, now in this nozzle, between location 1 and location 2, what has higher velocity? Location 2 has the higher velocity. How does it have higher velocity? Like, where is that energy coming from? Well, let's look at the elevations. Between 1 and 2, there's a little bit of a change in the z, but not enough to account for the velocity is so much faster at location 2. So what it means is that there's going to be a change in pressure as well between those 2 points. Since we have higher velocity at 2, since velocity went up, the pressure is going to go down at location 2. So the sum of these two terms is constant between the two locations. So if I wrote it P1 plus gamma Z1 plus density V1 squared divided by 2 is equal to each of those at the second location, P2 plus gamma Z2 plus density velocity at 2 squared divided by 2. What we're saying is as flow goes along a streamline in an inviscid fluid that's incompressible and conditions are steady, that there's an exchange in energy. That if you have the velocity go up, the pressure is going to go down, assuming that the elevation is relatively constant. Just to simplify things even further, I'm going to have location 1 and location 2 both be at the center line. Okay, so now the elevation doesn't change at all. Before it was changing a little just because of where I had picked my locations of interest, but if I'm at the center line of the pipe that's horizontal, so the Z1 and the Z2 terms cancel out. So that means if the velocity goes up at 2 because of the contracting diameter, then the pressure is going to go down. And that's sometimes what we call the Bernoulli effect, the lift over the top of a wing, because it has a higher velocity over the top of the wing, then that decreases the pressure, and that's what causes lift, is the difference in pressure between the top of the wing and the bottom of the wing. So we can write it in terms of the units over here. Each one of these terms is going to have units of newtons per meter squared. More commonly, I like to write Bernoulli's equation in terms of head, where the units are meters. And the reason for that ties into hydraulic models and the way that we can sometimes sketch where the energy is in a hydraulic model. But you can solve for the pressure or the elevation or the velocity at the locations according to either of those two versions of the equation. And it's applied to situations where there's a convective acceleration. So like a nozzle where the velocity is changing. Any questions so far about Bernoulli's equation? Yeah. I think both is on the formula sheet, if I'm not mistaken. But I gave a challenge a couple of years ago to a class. I told them I'd give students a 5-point bonus on the exam if they took it with no equation sheet. And even before I gave the students who did that the 5-point bonus, the people who just had the equations memorized did better anyway. There's really only a handful of equations for this next exam. There is Euler's equation, Bernoulli's equation, and the momentum equation. So, I mean, there's on the next exam, there's only really like 3 main ideas. So, but anyways, I think there's both on that formula sheet. Was there a question over here?
Yeah, I was just kind of thinking about that pipe. So that equation saying the pressure at the end is going to be less.
Less. And that's, It's counterintuitive, right? Because this is something that a lot of students say, well, when you've got water, it's forcing down into a smaller confined space, just kind of like maybe your instinct tells you, wouldn't the pressure be higher there? Just because it's got a smaller area for all of that flow to be going through. And so I understand the notion, but actually the pressure is lower in the confined section, and we can go into the lab and prove it, and we will go into the lab and prove it. We'll plug in a pressure gauge, and we'll watch as the pressure decreases at the confined, contracted section, and then the pressure goes back up again when what we'll have is it'll re-expand after going through a brief contracted section. So it's the opposite of what sometimes you might think. Bernoulli's equation says that energy has to come from somewhere. You know, for you to have an increase in velocity, you must have a decrease in pressure. And so let's apply that to an example. Let me write up here on the board the example that we're going to calculate. We have an expanding section in this first example. We've got a pipe where the initial diameter is such that we have a fast velocity, and it's transitioning to a location where we have a slow velocity. So here at location 1, the flow is coming in, the velocity is equal to 5.5 meters per second. And then here at location 2, the velocity that comes out is 0.6358 meters per second. So what I'd like you to find here is if we're given that P1 is equal to 400 kilopascals, then P2 is what? And we'll assume that location 1 and location 2 are horizontal. We're working with water, so that's incompressible. Now it's not inviscid, but the reason why it's still okay for us to use Bernoulli's equation is that location 1 and location 2 are pretty close together. So there's not going to be too much pipe friction between them. If they were really far apart, then there would be a pressure change due to the Bernoulli effect, and then also pressure change due to head loss, due to pipe friction. But here, they're close together, so we're neglecting the effects of energy loss due to pipe friction. So just use Bernoulli's equation to find out what is P2. All right, so the flow is coming in at 5.5. It exits at 0.6358 meters per second. So we start with Bernoulli's equation. P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G. Z1 and Z2 are equal since it's a horizontal pipe. So we can rearrange Bernoulli's equation to solve for P2. It's going to be P1 divided by gamma plus V1 squared divided by 2G minus V2 squared divided by 2G multiplied by gamma. Since P2 is the unknown, we're trying to isolate that variable on the left-hand side of the equation. So we'll just make the substitutions now. The pressure at 1 is given as 400,000 newtons per meter squared divided by the unit weight of fluid, 9810 newtons per meter cubed for water, plus the velocity at 1 is 5.5 meters per second. Square that divided by 2G. And then we subtract out the velocity head at 2. And that is 0.6358 meters per second squared divided by 2G. And then all of that is multiplied by the unit weight of water, 9810 newtons per meter cubed. Now, I like to calculate things in intermediate terms just to see like where the energy is. Like how much energy is there in the velocity head? How much energy is there in the pressure head? So here, this first term is working out to 40.775 meters of head. The second term, the velocity head at the inlet, that's 1.5418 meters of head at where the velocity was 1.5. And then here, once the water is slowed down, 0.0206 meters of head. So these are relative indications of how much energy there is at each of the terms. And what you'll see is that there isn't very much energy in water that's moving 0.63 meters per second. You know, for a matter of perspective, that's about 2 feet per second. And so, I mean, 2 feet per second is a pretty slow walk, so it's not like there's a lot of energy in that. But compare it to the pressure of 400 kilopascals, 40 meters of head. So it means that here there's a relatively minor exchange. You know, when you go ahead and solve for P2, the P2 that we're going to get is 414,923 newtons per meter squared. That increase in pressure from 400 to 414.9 kilopascals, it's because the velocity there was some extra energy in the velocity when it was fast compared to now when it's slow. So that explains why the pressure went up, is that the energy had to go somewhere. You know, the extra energy that we had as velocity initially, once that fluid slowed down, the energy that was in the velocity went into an increase in pressure. Everybody get the same answer? 414.9? Okay. Of course, I don't know if everybody heard the question earlier, like what's the difference between this form of the Bernoulli's equation and the form of the Bernoulli's equation that's in terms of the piezometric pressure. So P1 plus gamma Z1 plus V1 squared divided by 2 multiplied by the density. So if you just divide each term by gamma, then that's how you get the equation that's in terms of head. Yes? Yes. Yes, you will get the same answer if you did it this way versus if you did it the other way. Are there other questions related to this first example? Okay, now the next example is a little bit tricky. And it's because of the way that we're measuring the velocity of air in a contracting section. Is it okay for me to erase this? Has everybody got stuff copied down? All right. So for this next example, we have a contracting section, and we're trying to figure out what is the velocity of air by using a manometer. Okay, so let's say that we have a nozzle that's contracting, and what we have is a tube that's connected before it contracted, and it's pointing over here. Okay. So that the air that's going through here, it's going slow, and then because it contracted, it's speeding up, and some of the air is going to go inside of this tube and cause a deflection in the manometer fluid. So here we've got a manometer fluid, and we can measure some deflection in the manometer. Here the distance between the two is 10 centimeters, and we're just using water as the manometer fluid. So it's water. We've got 10 centimeters separating the two liquid surfaces. Now let's make sure, first of all, that this makes intuitive sense, the fact that it's lower on the right than it is on the left. do you see how the air that's coming through this contracted section, what it's basically doing is it's blowing into the opening of that tube. And so it's stagnating. Once it gets inside the tube, this is a static manometer. Manometers don't have fluid flowing through them. The way that they work is that they measure pressure differences by having static conditions inside the manometer. So the wind is going through this nozzle, but the wind isn't going into the manometer. It's just this manometer opening is measuring the difference in pressure between this opening at the wide section and this opening at the narrow section. But what you'll see is that the opening at the wide section isn't intercepting the flow, whereas the opening at the narrow section is intercepting the flow. So not only is it measuring a pressure difference, but also this opening that the streamlines are dead-ending at, it's also getting a relative indication of how much velocity there is at that secondary location. So let's just put some labels on here and start breaking it down a little bit. We've got location 1, where the section is wide. Location 2 is after it has narrowed, but before the opening of the manometer tube. And then here, I'm going to call the center of the manometer tube, I'm going to call that location T, just to mean like the tube. It's inside the tube. And the principle that's going to be applied here is that the energy at location 1 is equal to the energy at location 2, and that's equal to how much energy there is inside the opening of the tube. So the energy at each of the locations is constant. It's just changing forms. Remember, in the first example, we had some of the velocity being exchanged for an increase in pressure. So here, we're going to see the same kind of thing. We're going to have a change in velocity. We can already see that just by looking at it, that location 2 is going to have more velocity. So what is that going to tell us about the pressure? Between 1 and 2, what's going to happen to the pressure in order for the velocity to increase? The pressure has to go down at 2. So P2 should be less than P1. But then what happens is that all of the energy that exists as velocity on the outside of that tube opening, as soon as that fluid encounters the tube where conditions are static, what existed as kinetic energy is instantly exchanged for potential energy. So there's an increase in pressure inside the opening of that manometer tube because the wind just dead ends. And so all of that energy has to go somewhere. It can't just be lost. It has to be exchanged. And so the energy, since this is all in a horizontal plane, so z's are all equal, z1 is equal to z2 is equal to z at the tube. And so what that means is the energy has two components. So v, the velocity head, and the pressure head at 1 is equal to the velocity head and the pressure head at 2, which is equal to the velocity head and the pressure head at inside the tube. So what I can do is I can say that the energy at 1 is equal to how much energy there is inside the tube. And so, in other words, P1 divided by gamma plus V1 squared divided by 2G is equal to PT divided by gamma plus Vt squared divided by 2G. I've omitted the z terms from Bernoulli's equation just because all of the z's are equal. Any questions so far with how things are shaping up? Yeah. Yeah, it's measuring the pressure difference between 1 and at this location T. Yeah. It's higher at 1 than it is at 2, but remember, what happens between 2 and T? Between 2 and T, at 2 there was all this velocity that had to be turned into extra pressure because the wind just stops. And so you're right that the pressure at 2 is lower, but inside the tube, just on the other side, just a little bit further away from 2, there's a world of difference of where the energy is. Because at 2, there's lots of velocity and a little bit of pressure, but now at T, all of the velocity that was there before at 2 got exchanged into a little bit of additional pressure. So what I'm going to say here is that at T, there is no velocity. V sub T term, that doesn't exist because conditions inside the manometer are static. So in other words, we can say that we could rearrange this equation to make it in terms of P1 plus density V1 squared divided by 2 is equal to P sub T. Okay, so we could rearrange that to be PT minus P1 is equal to density velocity at 1 squared divided by 2. So in this example, we're going to need to use the density, and it's given that the density of air, this is air that's going through here, the density of air is 1.2 kilograms per cubic meter. And if we want to find the unit weight of that, of course, all we do is multiply it by G. So the unit weight of air then is 1.2 kilograms per cubic meter multiplied by 9.81 meters per second squared. So that's 11.77 newtons per meter cubed. And of course, we also know, since it's water that's in this manometer tube, we're going to want to have the water properties available for us. So the unit weight of water and the density of water. The density being 1,000 kilograms per cubic meter, and the unit weight being 9810 newtons per meter cubed. How do we find the pressure difference inside the manometer? What equation do we use for that? Hydrostatic, that's right. Conditions are static in that manometer, so to describe the difference in pressure in the manometer, we're going to use the hydrostatic equation. Does everybody get how we got to this point? This difference in pressure between location 1 and location T? The difference in pressure is just, that's what the Bernoulli equation says, is that all of the velocity that there was at 1 got exchanged into an increase in pressure. That since there's no velocity inside that tube, that whatever energy there was at velocity is responsible for the pressure difference between the 2 points. Okay, so the last step then is for us to combine Bernoulli's equation and the manometer equation, which is the hydrostatic equation, to combine those two together. Okay, so the manometer equation is saying that P1 plus gamma, delta H times gamma is equal to P sub T. So here we are at location 1, and in gases the pressure doesn't change very much when we move up and down through a gas. And so what we're saying is since location 1 is in the center of the pipe, the pressure at the center of the pipe is pretty close to the pressure here at the interface of the air and the water on the left side of the manometer. So we're saying that P1 plus this delta H of 10 centimeters working through the unit weight of the fluid is equal to P sub T. So the pressure in the right-hand side of this manometer tube is the same everywhere because we're in a gas, so the pressure isn't changing. So right here is P sub T, and everywhere through the tube we also have P sub T approximately. I mean, if we're talking like a kilometer, then the pressure is going to change in a gas, but not in a couple dozen centimeters. So over here, the manometer equation allows us to rearrange this to find P sub T minus P1 is equal to delta H times gamma. And our delta H was 10 centimeters, which is 0.10 meters. And the unit weight is 9810 newtons per meter cubed. So it's 981 Newton per meter squared. That's the pressure difference between the two. And if we go back over here, when we were using Bernoulli's equation, what we had was the difference in pressure. So we could rearrange this equation. We could solve for V1. If we did, V1 is equal to 2 times PT minus P1 divided by the density to the 1/2 power. Okay, so move the 2 over, divide by the density, and take the square root of both sides. So that's where this came from. This is our Bernoulli's equation. And we put them together. The manometer is where we were measuring the pressure difference. We put the manometer pressure difference that's indicated into Bernoulli's. And so why don't you do that and see if you can find what is V1, and then also what is V2 if it's given that the area at that A1 is twice A2. So what that means then is that V2 is going to be twice V1. Good, that's right. Yes. All right, so this was a complicated problem where we're putting together two ideas at once. We're using the combination of Bernoulli's equation and the manometer equation, and you're going to find that trend accelerate. There will be fewer and fewer problems where it's just a single idea, and more of them where you have to combine two concepts together in order to solve for the right answer. And so here, the two ideas that we're putting together is we are measuring the pressure difference using a manometer, and then that pressure difference is caused by the Bernoulli effect inside that converging section. But then the tricky thing that students really struggle with is the idea that what's the difference between location 2 and location T? And that opening of the manometer tube is a stagnation point, where all of the wind to the left of the stagnation point has velocity, but then when the wind dead ends at the opening of that stagnation point, the pressure instantly goes up a lot because all of the energy that existed as the velocity at location 2 is instead exchanged for an additional increase in pressure at location T, and then the assumption that the pressure inside the manometer tube where we've got gases is constant. It's just in the liquid section that the pressure is varying appreciably. So this differential manometer is telling us the difference in pressure, but then it's also encountering those dead-ending streamlines, which allows us to capture the velocity head as well. So any questions from this example? All right. Well, you've got a homework assignment that's due on Tuesday, and I've got office hours this afternoon. If you'd like to stop by, I'd be happy to see you. There are a handful of you who still haven't picked up your exams, so if you want to get that from me, I am headed back to my office right now if you'd like to collect your exam and haven't done that yet. Otherwise, have a great day. I'll see you on Tuesday.